Hello and welcome to this series of lightning talks by various ScyllaDB developers. And we'll begin with Asias with a talk about repair-based node operations. And just a reminder, a node operation is when you bootstrap or decommission a node, and we've done some work to move that to using repair instead of using streaming, and Asias will explain how and why. So here's Asias.
Hi everyone, welcome to my talk. This is Asius here. In this talk, I will cover repair-based node operations itself and two more related features of strategic compaction and gossip-free node operations. First, what is repair-based node operations? It is a new feature to use zone-level repair as an underlying mechanism to sync data between nodes instead of the streaming for node operations like add or remove a node. There are multiple benefits of using repair-based node operations. It has significant improvements on both performance and data safety. For example, we can resume from a failed bootstrap operation without transferring data already synced on this node to speed up the operation. It also guarantees that the replacing node has native replica to avoid data consistency issues. It also simplifies the procedures so that there is no need to run repair before or after operations like replace or remove node. Another benefit is that we can use the same mechanism for all the node operations. We have enabled repair-based node operations by default for the replace operation. We will enable more operations by default in the future. All node operations are supported. We have added options to turn on specific node operations. For instance, here below, we enabled both replace and bootstrap to use this feature. In addition, we are improving the IO scheduler to make sure the node operations will have less latency impact as possible, so we can enable more operations by default. You will hear more about the IO scheduler work from Pavel and Avi's talk. The idea of strategic compaction is to make compaction during node operations more efficient to speed up the node operations. It keeps the SS tables generated by operations in a separate dataset, only compact them together when the operation is done. Then it integrates the new SS tables into the main set. It is more efficient this way than adding the SS tables into main set as soon as it is generated. As a result, we will have less compaction work during node operations, and we can make it faster to complete node operations. We have enabled off-strategy compaction for all the node operations. For repair, we will wait for a while for more repairs to come to trigger off-strategy compaction. For other operations, we will trigger immediately at the end of the operations. This is all automatic. No action is needed by users to enjoy this feature. Last but not least, I will talk about the gossip-free node operations. It is a new feature to use RPC verbs instead of gossip status to perform operations like add or remove node. The feature gives multiple benefits. First, it is safe to run node operations by default. It requires all the nodes in the cluster to participate in topology changes. This avoids data consistency issues if nodes are network partitioned. For example, if a node is partitioned and not aware of the bootstrap operation, this node will use the wrong token ring to route traffic, which can cause data inconsistency issue. In case that the nodes are really gone and dead, the user do want to run node operations, we have introduced the ignore dead nodes option to allow it. Another important improvement is that with this feature, all the nodes in the cluster can revert to a previous state automatically in case of error during operations. For example, when a replace operation failed, the existing nodes will remove replacing node as a pending node immediately and automatically, as if the replace operation were not performed. At the moment, it is not allowed to add more nodes in parallel or perform multiple nodes operations at the same time. With this feature, we can reliably detect if there is any pending operations to avoid operation mistakes. Each operation is now assigned with a user ID to make it easier to identify node operations cluster-wide. We have enabled this feature for Bootstrap, replace, decommission, and remove node operations. No user action is needed to use it. Thank you.
So thanks, Asius. And the next feature is quite an exciting one, repair-based Tombstone garbage collection. And this is exciting because repair can be a stressful feature to manage. If you lag behind your repairs, then you run the risk of data resurrection, and nobody wants that. So we came up with the repair-based Tombstone garbage collection, which allows the database to track the times when you ran repair and to manage Tombstone purging by itself. So here's Asius again with an explanation of repair-based Tombstone garbage collection.
In this talk, I will first cover the background of tombstones in Scylla, explain the current timeout-based tombstone GC method, and introduce the new repair-based GC method. Tombstones in Scylla are used to delete data. Normally, data and the tombstones are replicated to multiple nodes. Another thing to note is that we could not keep tombstones forever. Otherwise, if we have a lot of deletes, the database will contain unlimited amount of tombstones. The solution to this problem is that we drop the tombstones if they are not necessary anymore. Currently, we drop the tombstones when the following happens. First, the data covered by the tombstones and the tombstones can compact away together. Second, the tombstones is old enough. It is older than GC seconds operation, which is 10 days by default. However, the tombstones might be missed on some of the replica nodes. For instance, the nodes was done and no repair was performed within GC seconds. As a result, data resurrection could happen. For example, nodes with tombstones to GC, tombstones and the covered data are gone. The node did not receive the tombstones still have the data that is deleted. In the end, a read could return deleted data to the user. I will call the current GC method timeout-based tombstone GC. With this method, users have to run full cluster-wide repair within GC seconds. This GC method is not robust because the correctness depends on the cluster operations, and nothing guarantees if one can finish repair in time. Since repair is a maintenance operation and it has lowest priority, if there are important tasks like user workload and compaction, repair will be slowed down. This adds pressure to people who operate Scylla to finish repair within GC seconds. In practice, users may want to avoid repair to reduce performance impact and serve more user workloads during critical period, for instance during holidays. So we need a more robust solution. We implemented the repair-based tombstone GC method to solve this problem. The idea is that we GC tombstones only after repair is performed. This guarantees that all replica nodes have the tombstones, no matter if the repair is finished within GC seconds or not. This brings multiple benefits. With this feature, there is no need to figure out a proper GC seconds number. In fact, it's very hard to find a proper one which works for all the workloads. And there is no more data resurrection if repair was not performed in time. So we have less pressure to run repair in a timely manner. As a result, we can throttle repair intensity even more to reduce latency impact on the user workload, since there is no more hardware requirement to finish repair in time. If repair is performed more frequently than GC equals second, tombstones can be GC'd faster, which gives better read performance. We can use alter table and create table to turn on this feature. We have introduced a new option, Tombstone GC, which can specify the following modes. The first one, timeout, which means GC after GC equals seconds. This is the same as before this feature. Repair means GC after repair is performed, and disabled means never GC, and the immediate, which means GC immediately without waiting for repair or timeout. When to use the immediate mode, this is mostly useful for time window compaction strategy with no user deletes. It is much safer than setting the GC equals seconds to 0. We are even considering to reject user deletes if the mode is immediate to be on the safe side. The disabled mode is useful when loading data into Scylla, since the tools can generate out of order writes and writes in the past, and we do not want to run GC when only parts of the data is available. In such cases, we can set the mode to disabled when the tools are still loading data. In extreme cases, if a repair cannot be finished for some reason, we can introduce a new API to fake repair history as an emergency to allow GC. A new gospel feature flag is introduced. A cluster will not use this feature until all the nodes have been upgraded. Also, the default mode is timeout. Users have to set the mode to repair explicitly to turn on this feature. That's it. Thank you so much.
Thanks, Asias. And next up is Rafael with some new improvements that we made to compaction with changes to time window compaction strategy to simplify data modeling for time series, and also improvements for incremental compaction strategy, allowing you to manage space simplification with incremental compaction. Rafael?
Hello everyone and welcome to my talk about stable compaction enhancements. My name is Rafael Carvalho and I have been working on ScyllaDB storage layer since its early days. Enough about me, let's move on to the interesting part. In this session, we'll describe space optimization for incremental compaction that will allow storage density of nodes to increase. Additionally, how Scylla makes it much easier to model time series data without having to rely on old techniques like data bucketing, which is commonly used to avoid running into large partition performance issues. Last but not least, we'll talk about upcoming improvements that will make compaction even better for you. Now let's take a look back. Incremental compaction strategy, or ICS, was introduced back in 2019 to solve the large space overhead that affects most of the users. Before its existence, users were left with no choice but to leave 50% of free disk space for compaction to succeed. But was it enough? Well, the aforementioned space overhead was efficiently fixed by incremental compaction. However, it suffered with bad space amplification when facing overwrite-heavy workloads. That's because the compaction strategy wasn't efficient at removing the data redundancy accumulated across the tiers. We used a theoretical module called run conjecture to reason about compaction efficiency. It states that a compaction strategy cannot be optimal at all the three efficiency goals: read, write, and space. That's why we have different strategies available, each suiting better a particular use case. If we look at the three-dimensional efficiency space, which represents the run conjecture, trade-offs, we'll see that incremental and side-tiered strategies cover a similar region. Turns out incremental compaction can do much better than fixing the space overhead problem aforementioned. We know for a fact that leveled and size-tiered strategies cover completely different regions in the efficient space. Also, we know that interesting regions cannot be reached with either of them. However, very interesting regions in the efficient space can be reached by combining the concepts of both strategies. We call it a hybrid approach. What do we actually want to accomplish with this hybrid approach? Let's set a few high-level goals. Firstly, we want to optimize space efficiency for override workloads, while ensuring write and read latency meet service level requirements. In other words, performance must be sufficient to meet the needs, but space efficiency should be as good as possible to allow for scale. That's space amplification goal for you. A feature that will help you increasing storage density per node, therefore reducing the cost. Who doesn't like that? It's only available in Scylla Enterprise and can be used with our incremental compaction only. Everything was carefully implemented. To ensure latency will meet service level requirements, compaction will dynamically adapt to the workload. Under heavy write load, compaction strategy will enter a write optimized mode to make sure the system can keep up with the write rate. Otherwise, the strategy will be continuously working to optimize space efficiency. The coexistence of both modes is the reason we call this a hybrid approach. The adaptive approach combined with the hybrid one is what makes this feature so unique in the compaction world. Let's get to a bit of action. How to enable the space optimization? That's simply a matter of specifying a value between 1 and 2 to the strategy option named space amplification goal. The lower the value, the lower the space amplification, but the higher the write amplification. 1.5 is a good value to start with. In order to optimize space efficiency, we are willing to trade off extra write amplification. However, the adaptive approach minimizes the impact of the extra amplification, given that the strategy will switch between the available modes, that is, write and space, whenever it has to. To summarize, this will nicely give user control to reach interesting regions in the efficiency space, allowing the strategy to perform better for your particular use case. Now comes the interesting part, the optimization in action. We can clearly see in the graph that the lower the configured value, the lower the disk usage will be. In the example with a value of 1.25, the space amplification reached a maximum of 100%, but eventually it went below the 50% mark. If the system isn't under heavy write load, the space amplification will meet the goal faster. As expected, the system is optimizing for space once performance objectives are achieved. Now let's switch gears and talk about how Scylla made time series less painful for application developers. Please look at that great table statement. That's an unusual schema for time series data. Note how the field date composes the partition key along with the sensor ID. That's a technique called data bucketing. This bucketing technique is mainly used to prevent large partitions from being created, as they were known to creating all sorts of performance issues. For example, Scylla was very inefficient when reading from the middle of large partition. Also, repair was an enemy of large partitions, and time window compaction strategy wasn't optimized for reading a large partition spanning multiple time windows. In the picture, each individual line represents a partition. In the bucketed case, the time series is split into multiple smaller partitions, while in the unbucketed case, the time series is kept in a single partition. One of the main problems with the bucketing is that lots of complexity is pushed to the application side. The application will have to keep track of all partitions that belong to a particular time series. Also, aggregation is more complex as the application has to figure out which partitions store a particular time range, query each one of them individually, and finally aggregate the results. Fortunately, those bad days are gone. Scylla fixed all problems aforementioned. Large partitions can now be efficiently indexed. Row level repair was introduced to solve the problem of repairing large partitions, and the time window strategy can now efficiently read large partitions stored across multiple time windows. When a table uses time window strategy, its access table files are not going to overlap in timestamp range. So a specialized reader was implemented that will discard irrelevant files and efficiently read the relevant ones. This will reduce resource consumption and read amplification, making the queries much more efficient. With all those problems fixed, the schema for time series application can now look much simpler. Queries become simpler, your application becomes simpler. Please only make sure you have enough time series partitions to avoid hotspots, where a subset of shards may be processing much more data than its counterparts. For example, if your application is monitoring millions of devices, where each has its own time series, then you will not run into any unbalanced issue. But if you only have few time series in your application, it's better to rely, unfortunately, on the old bucketing technique to guarantee proper balancing. As for the upcoming improvements, cleanup and major compaction will now be more resilient when the system is running out of disk space. Additionally, now the compaction manager will dynamically control the compaction fan-in. Essentially, it is a threshold on the minimum number of input files for compaction to increase the overall compaction efficiency, and that translates into lower write amplification. This decision is based on the observation that compaction efficiency is a function of on the amount of input files for compaction and also their relative sizes. That's why size tiered and ICS favor similar sized files to be compacted together. Essentially, we will increase the overall efficiency by not diluting the efficiency with compaction jobs that are less efficient than the ongoing compaction jobs. The system becomes more stable and performant as a result of this change. Last but not least, the I/O scheduler is being nicely enhanced by Pavel Emelianov. The enhancement will make the system more stable, allowing compaction to impact less the other activity in the system like user queries, streaming, and so on. To learn more about this, you can watch Pavel's talk. And off-strategy compaction was written with the goal of making compaction less aggressive for node operations like bootstrap and regular repair, allowing them to complete faster. Consequently, the system will be able to scale faster, making Scylla elasticity even better. Thank you for watching. See you around.
Thanks, Rafael. So that's it for this series of lightning talks about ScyllaDB 5.0. We hope you enjoyed them, and we'll be working on more feature for next year so we can present them in Scylla Summit 2023. Thanks, everyone.